Okay, let's start with the second half of the lecture. I wanted to ask something, but I forgot what it was. Okay, so some set x here finite has 2 to the n minus 1 odd sets and even sets as well. Yeah, so yesterday evening I went and made my notes up until section 3.6 because I'm like, I'm not sure I have enough material, and then people get bored. And I think we're barely managing it to section 3.3. So yeah, it's hard to estimate for how much we can manage. And then at some point, I guess, if I go at that speed, I have to either skip some parts or maybe make it for home reading. I have to see. Yeah. So we want to show that the number of odd sets or even sets is 2 to the n minus 1. And again, we describe a projection from 2 to the x except one element a to the odd sets. And this projection goes as follows. A is mapped to A if A is odd, and to A union little a if A is even. And again, we have to show that the projection. So we have to show, I always forget these names, 1 to 1. You're used to some terminology, it's difficult to adjust to a different one. So yeah, no two sets A are mapped to the same set here. If I have some A and B, yeah, if they both contain, if they're both odd, they just go to itself. If one of them is even and the other is odd, then the image of one will contain this little element A. If they're both even, yeah, they're both getting contained as well. I think it's clear that 1 to 1, and then we have to show that it's onto or surjective. So take any odd set, right? If it doesn't contain A, so little a here, then the pre-image is just itself. If it does contain little, if it's take any odd set, take the pre-image, that should be fine. If you have if it's contains some little a, then remove that, and then you get the even set here. That made sense? Or that was too hand wavy? Should I make it more formal? Okay. Okay, so let B be odd. Case 1, A is not element B, then phi of B equals B. Case 2, A is element B, then phi of B without A is B. So B without A is an even set, so we will add A to it. Now happy? And the tombstone, okay. So now we go to injective mappings. So what's the number of functions x that map into y? So this type of error is meant for injective. I can also write it. So I shouldn't write injective. I should write, maybe I just write injective because otherwise I go crazy. And then you also learn two different terminologies for the same thing. And that number is m times m-1 times m minus n plus 1. And here, this has size n and this has size. Yeah. Proof. So again, proof by induction. N equals 0 is kind of trivial. So I guess n equals 1, we have m and that's fine. So we do the induction step from n to n plus 1. And I guess the what happened there is that we have this big set x and this big set y. And we fix some element here. And it has n possibilities to go here. And then what remains here, these are n minus 1. And here, these are n minus 1. And so you still have to map all of those to the green stuff. You're not allowed to use this because otherwise you wouldn't be injective. And then just multiplying out those things. So we have then m possibilities for the red element times, and now we use the induction hypothesis. What are number of functions from map from here to there? And this is n minus 1 times. Oh, sorry, I went from n to n plus 1. So here's still n remaining, but this is n minus 1. So we have n minus 1 up until n minus 1 minus n. Is this correct? And then that's the same as m minus 1 times n minus n plus 1. plus 1. So I just moved this minus 1 into here, and then it has exactly the shape of that thing with n plus 1 instead. I have to say I'm not a huge fan of all of those proofs because I think they are more or less the same. But yeah, so I want to follow very closely this book because then people can just read that book, and I think that's a good thing. But yeah, by the way, so for these types of proofs, should I maybe skip them in the future and say, okay, this is something you can do, or is it good to see this once? You think it's good to see it once? Okay, then let's keep it. Questions to that proof? Yeah.
Yeah, where does the minus 1 come from in the induction? N minus 1.
So here we have the set y has size n, right? So this would go for any n. But one of the elements is not working, so we get here n minus 1. So we start here with n minus 1, and then have still this n minus 1. That set here has size n, so we subtract n, and then we add this plus 1 just to have the same size. It's really an exercise of fitting in numbers in the right way, but that's the argument here. All possibilities to map this thing to there, and then the remaining possibilities to map that to the remaining. Okay, thanks for the question. Okay, so a permutation is just a mapping from a set to itself. So it's just a bijection. And x is typically finite. I think if x is not finite, we would not use the term bijection. We would not use the term permutation. And so x does not need to be the set 1 to n, but usually it's just for simplification. If we want to talk about it, it's easier to just say. So it's more of a convention that x equals. But yeah, you can also have bijections or permutations of other sets. You can say I have 3 students. Let's permute them how they sit. Yeah. Okay. And so we have then cycles. I'll draw here some nice cycles. So there are ways to represent permutations. But we can just write down their cycles, right? And maybe it's 1, 5, 2, 3, 6, and then we have 4, and then we have 7, 9, 8. That could be all the elements. So the error of each element shows us where this element is mapped to, and then we can see those cycles. And we can also write permutations in a different way. So we can say okay, 1 is mapped to 5, 5 to 2, 2 to 3, 3 to 6, and 6 is back to 1. So then this is kind of a cycle here. So that's one way of using notation. So 4 would go to 4, and 7 to 9, 8 to 7, and 9 to 8. That would be another cycle. But you can also write down this in the cycle notation, which is 1, 5, 2, 3, 6, 4, 7, 9, 8. So here we write down every cycle. This is cycle notation. Okay, I think that was it, what I wanted to say about permutations. It's more of a definition. There are some curious puzzles about permutations, and I guess assume at least the mathematicians all have heard already of permutations, right? Okay. By the way, so I wanted to ask also one thing. So who of you is in their first year of studying? Okay, second year? Third year? Okay, so most are third year. Okay. Yeah, so one of the things that I thought is that maybe it makes sense for have the mathematicians to take this course as a second year course and not as a third year course. But maybe you can tell me at the end of the course if that makes sense or not. Okay, so binomial coefficients, I guess most of you have heard of them as well. I'm seeing some nodding. So n choose k. By the way, this is really confusing, I think, for German and Dutch speakers, so to all of us. Because in English you say n choose k. In German you say n über k. How do you say it in Dutch? Over. Or? Boven. N? Boven, okay. So the same as über in a sense. The problem is the English n over k, n over k as n divided by k. So that regularly leads to confusion. So that's why sometimes I may say n over k when I really mean n choose k, just because of my German. Okay, but it is just defined as n factorial divided by k factorial times n minus k factorial. Aha, I haven't actually written down factorial. So who does not know what factorials are? Okay, everyone knows, very good. And then we can also write x choose k. So here x is a set. And that's the set of a subset x such that the size of A holds k. So the subset of size k. And the first thing we're going to prove, that's proposition 3.2.2, is that x choose k, so all subsets of size k is the same as x choose k. So this is a formula. That's the number of sets and their cardinality. Subtle difference. But I mean, it looks like almost the same, but that's kind of the point. So it justifies this notation there. Okay, here, size of x, and again. And the proof is easy. We look at the number of ordered sets. Ordered sets of size k. And this we already know as n factorial divided by n minus k factorial. How do we know this? As a hint, we've proven this in the lecture, but not in, we haven't called it like that. It's proposition 3.14. Here, just with a set x in that case would be of size k with the numbers 1 to k, and then this gives us the ordering of the number. Okay, but that's the same as the number of unordered sets of size k times k factorial. Why times k factorial? Because if I have an unordered set, there are k factorial many ways to make it an ordered set, and I would always lead to a different ordered set. And then we move that to the other side, and then we're done. Questions? Okay, so this was not a proposition, but more of a remark, but let's keep it here. Number of ways to have R integers is 0. So I could write natural numbers, but I'm never sure who includes a 0 and who not. So just write integers larger equal to 0 that add up to 1. And here it's kind of meant with ordered integers. So we give an example. So maybe n equals 5, and then we would have, that's already too large. N equals 4, and then we had to have, let's say R equals 3. Then we have 0 plus 0 plus 4, or 0 plus 4 plus 0, or we had to have 1 plus 2 plus 1, and so on. So is it clear what I mean with integers adding up, R integers adding up to n? So the order of those integers matters as well. And then so this is more of an explanation here. So, and then this is the same as n plus R minus 1, R minus 1. I'm not sure if my R's are particularly legible, but I'm not really sure how I can draw them in a better way. Maybe I should go to Q's, then I erase R's out of my alphabet, yes? Thank you. That makes more sense, yeah. Otherwise, there would be very few possibilities. Okay, and this proof, so Matousek says it's a little bit of a, how to say this, of a little bit of a magic trick how it looks like. And I would say it's just a very cute way. So we want to have these integers, and let's say we have here 1 plus 0 plus 3 plus 2 plus 0. Okay, just giving you one of those. And they add up to 6. So I have 1, 2, 3, 4, 5 boxes. Wait, yes, I have 5 boxes. So let me draw those 5 boxes. 1, 2, 3, 4, 5. And here I put in 1. Here that box stays empty. This box I put in 3 guys. This box I put 2 guys. And this box stays empty again. Just a different way of representing that thing, right? Now I use an eraser, but the way I use the eraser, I just draw it again. I just erase the bottom part and the left and the right. Now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 symbols are and 4 lines and 6 dots. And now what I can see is I can choose 4 possibilities to move those lines between the dots. And now you have to do the math, but that exactly is this formula. So this is here r minus 1. This is n, and this is n plus r minus 1. Yeah, I think this is one of the maybe the nicer proofs that we have. I think at the beginning of each course you have to deal with a lot of tedious things, right? Proof by induction, as we did already. But already here we can come to such a more elegant statement and proof. Okay, so there are some basic properties of binomial coefficients. So we have n choose k equals n choose n minus k, and this comes from the definition. There's also a combinatorial proof of that, which is we can look at all subsets of size k, and that must be the same as all subsets of size n minus k, because we can have a mapping, a bijective mapping from if I take a subset of size k, take its complement, and it has size n minus k. So and then there is this formula n minus 1, choose k minus 1 plus n minus 1, choose k. We try to draw this is n choose k. Again, there is a nice combinatorial way. If I have the subsets of size k, let's say I have the set x equals 1 to n, and I want to look at all subsets of size n. I can look at those that contain 1. They're n minus 1 choose k minus 1, many of them. Right? The remaining k minus 1, I choose out of the remaining n minus 1. Or they could not contain 1. Then I have to choose k out of them on the set of size n minus 1. That was maybe too fast. Okay, maybe I do that a little bit more formally as well. Okay, and then we can draw this Pascal's triangle. And here, I don't really know what is Pascal's triangle. I mean, I can draw it, but and I know what each entry means. But I guess it's a pure way of illustrating. Oh, that's wrong. So here I just write all binomial coefficients in a specific way. And the way the very left ones are ones, the very right ones are ones. And then for each entry in the middle, I just can get that entry by adding up its parents. I think this most people have seen at school, at least in Germany, we've seen that at school. And it sometimes can be helpful to think about these binomial coefficients. Yeah, so maybe one thing I should also mention is, I guess you've seen in the course manual that there will be guest lectures. So the purpose of these guest lectures, so I moved this course to be more, let's say, on topic with discrete mathematics. And then people complain, oh, but how do we see that this is a computer science course? So you will see some applications of where researchers use discrete mathematics in different parts. And yeah, this will also be part of the exam, but I hope you will find that interesting. Aha. So I think Matousek doesn't give this proof here, but there are two possible ways to prove this. A boring way by induction, or combinatorially. Yeah, so I think none of them is in the exercise, so I can I guess sketch it. If you write this out, right, then each factor either has a 1 or an x there. And then you can choose if you want to have x to the k, then you have to choose x k times. So it's you have get it and choose k times. That's a combinatorial proof. And the proof by induction, yeah, I mean, you use the this identity that I just showed to you. I shouldn't write here proof. I should say idea, because I'm not really writing a proof. And so binomial theorem is really useful. Actually, also sometimes in ways that you wouldn't expect. So we had this kind of annoying proof by the number of even sets of size 2 to the n. Even sets equals -1. And using the binomial coefficients, there's a better way to do it. So we write n choose 0 plus n choose 1 plus n choose, oh no, sorry. We alternate minus, plus, minus, and so on. And that's 1 minus 1 to the n. That's just the binomial theorem with x equals -1. So we alternate. And then we write here n choose 0 plus n choose 1 plus n choose 2. And those are 2 to the n. Now, if we add them up, we get 2 times n choose 0 plus 2 times n choose 2, and so on, which is 2 times number of even sets. And in this way, we can show that the number of even sets is 2 to the n minus 1. Okay, let's do a last proof, and then I think we're done for today. Okay, this upper part of this whiteboard is not working. So we have this. Am I right in the ordering? Yes, okay. Yeah, so I guess the point here of Matousek was to say that with a lot of binomial identities, and he just gives one example, but there are many more. What we can do is if we have 2 n elements, so n here and n there, and we want to collect n of them, we collect I of here and n minus I of here. That's the way to collect n elements, right? Out of 2 n elements. So that would be the sum. So 2n choose n is therefore the sum over all I of n choose I times n choose n minus I. And that's the same as n choose I squared, because we can plug that here. Okay, I think, do we have still time for something teeny tiny? Okay. Maybe not. So let me just use the last 2 minutes to ask you, is the speed of this lecture too fast? Too slow? Is all right? Okay, so I guess majority, we have some outliers. Actually, how to say this? The variance of the distribution is small, so that's good. I make me a note where I finished. And then see you in the tutorial, because I will also show up in the tutorial. But otherwise, next lecture is on Monday.